you tell us the ones that we have to skip? Because you said that.
Well, this is sample test number 2. Because what I didn't cover for the second example was redox reactions. So we're going to go back to sample test 2, and then we'll look at sample test 3, and I'll tell you what to skip. For sample test number 2, we'll start with number 5 here. Oxidizers are electron poor, true or false? Oxidizers are electron poor. What do oxidizers want? Is it true? Or false? Or can't tell? False. Okay, let's put it this way. Oxidizers are electron rich. Well, if they aren't poor, they must be rich. Are oxidizers electron rich? That's oxygen ion is 2 minus. Oxygen 2 minus is called oxide. So oxide's a powerful oxidizer. Let me give you an example of oxide, like in water. In water, the oxidation state of oxygen is -2. Good oxidizer, water. Oxygen is a good oxidizer, but oxygen is not -2. Oxygen is 0. It's true. Oxidizers are electron poor. It's true. CH4 methane is a neutral molecule that is best classified as electron rich. True, you think? It's not an ion. That's what I mean by neutral. So it doesn't have a positive charge or negative charge. Maybe, so this may be false because maybe it's not electron rich. It's not electron rich, it's not electron poor, it's just neutral. Methane's just happy as is. Like helium, you know? Helium's just happy as is. Doesn't want to burn. He doesn't want to burn anything. Helium just. This is why kids can play with helium balloons. Kids can play with helium balloons because the worst that's going to happen is it's going to pop. But it's not going to poison the kids because helium is not going to burn. It's not going to burn anything. This is going to take some time. We don't have that much time, so somebody take a guess. False? Anybody say true? If you want to understand redox properties, do we look at the octet? No. If you want to understand redox properties, do you look at formal charge? No. If you want to understand redox properties, you look at what? Not the octet, not the formal charge. I mean, methane's a pretty simple structure. It's carbon in the center with 4 hydrogens. Carbon's 4 electrons, each hydrogen's 1 electron. This is octet. We could see, you know, in organic chemistry, we would look at this and see that carbon contributed 4, it got 4 back in the structure. Each hydrogen contributed 1, it got 1 back. structure. So I wouldn't even need to total up the electrons. I can just see right off that the number of electrons is correct. It's 8 electrons total. So does the octet tell us anything about redox? No. This formal charge. What are the formal charges here? They're all 0. What tells us about the redox? There are 3 ways of counting electrons. You know, the thing is, the best thing is to like, you know, and this is what I found to be a tremendous stress reducer, because I have a tendency to procrastinate and then just cram everything at the end, which causes a lot of stress. But it's better, you know, if you kind of learn it as you go along. So I had to really work hard to change that. I'm still not very good at not procrastinating. But one of the things as a student, it's easier to do because on quarter systems, if you're at UCLA, you're on a quarter system only 10 weeks long. You don't have time. Try to stay on top of the material, review it. That way, you know, when I switched over to the other method of studying, I didn't have to really review for the final. I already had it memorized. The material that I needed memorized. I know I just talked about this the other day, about how, you know, there are 3 ways of counting electrons in the Lewis structure. 1, Lewis octet. 2, formal charge. 3, oxidation state. How many times have I said, if you want to understand redox properties, you have to look at the net charge? No, you look at the oxidation state. How many times have I said that? Well, I don't actually remember, but that's what we've got to look at. We got to look at the oxidation state, and that's how we know. It's not a guess. I don't look at methane and go, I'm going to guess, you know, flip a coin. What I do automatically when I look at methane, I figure out what is its oxidation state. What are the oxidation states? Oxidation state's not a 50-50 share like this. What is oxidation state? Oxidation state is, we call, 100%. Winner take all. So who wins? Carbon or hydrogen? Carbon wins all. And so that means carbon ends up being pretty rich with how many electrons? With 2, 4, 6, 8. It got all 8 electrons. If carbon ends up with all 8 electrons, how many electrons did it contribute? It only contributed 4. So it got 8. And so that means it's going to have an oxidation state of -4. Hydrogen lost. Hydrogen lost. Hydrogen lost. Hydrogen, all the hydrogens +1. Carbon's a -4. Do you consider that electron rich, or do you consider it electron poor, or what do you consider it? Or you can't tell? Like, okay, let's compare it. We need to compare it to something. Let's compare it to CO2. Electron rich and electron poor are relative terms. You have to memorize the extremes. And the extremes are this. Winner take all. Who's the winner here? Carbon versus oxygen. Oxygen. Oxygen takes all 8. I mean, it has 8 now. It's -2. Contributed 6. Carbon ends up with 0. Carbon ends up with no electrons. How many electrons did it contribute to the Lewis structure? 4. It ends up with 0, its charge is +4. So at one of the end of the spectrum, we say it's electron rich, potentially. Carbon's charge varies from what? Oxidation state varies from? Carbon's oxidation state varies from? -4 to +4. So -4 is on the rich end, +4 is on the poor end. Now, whether it's rich or not depends on its behavior. For example, oxygen varies from +6 to -2, but oxygen at -2 is happy as is. It's not very rich. It's hard to burn this. It's hard to burn water. But it's easy to burn methane. Methane's easy to burn. Anyway, I don't have time to go back through and re-explain everything. And so just let me know which ones you want to go back through, or just hit it as is. This is electron rich, so everybody would have gotten it false. Everybody who said false is wrong. Everybody who said true would have gotten it right. This would be electron rich. Electron rich. And so I'm part of the redox thing. So this is the type of stuff you end up cramming, at the last minute, but it's too much to cram, so this is why it creates a lot of stress. 7, element plus element combination decomposition, single replacement, and combustion reactions are redox reactions. Sure. Titanium 4 ions and sulfate ions will precipitate. This is metathesis. 9, oxidation state charge on chlorine and ClO4 minus is +7, correct. H plus can react with silver metal. This is redox. H plus can react with silver metal. I showed you the shortcut way and I showed you the long way. Let's go back to the shortcut way. Do you guys remember it? Or you don't remember it? If I take H plus and I oxidize lead, if I take H plus oxidized lead, I'm going to form lead 2 plus. So lead 2 plus will be the product. So I'm going from stronger to weaker, or weaker to stronger. H plus to lead 2 plus. Strong to weak. And so that means H plus can oxidize anything that's stronger than hydrogen. And so H plus can oxidize tin, because if H plus oxidizes tin, I'm going to form tin 2. Well, tin 2 is weaker. Do you guys remember this? And so what we can do is we can just look at the chart. Where's silver? Silver's up there. So if H plus reacts with silver, I'm going to form Ag plus. Is Ag plus stronger or weaker oxidizer than H plus? Stronger. Fluorine's the strongest of the five. And so that means that we're going from weaker to stronger. Is that driving force? No. H plus can react with silver metal, false. Did anybody go through these questions? Because this isn't the purpose. The purpose of this is not for me to repeat what I said earlier, because if I just repeat what I said earlier, it might not catch. It's like earlier, did you remember what I said earlier? No, maybe not. You can forget it easily. And so the way to make this memorable is not for me to repeat it like 2 times, 3 times, although they say if you repeat things 3 times, it's best. problem. The best is if you give it some thought first and then, because what happens is if I repeat it, then of course it's going to be easy because I've done these so many times. I've done these types of problems so much, What you have to see is, okay, where do you get stuck? That's what you need to find out. How you find out where you get stuck is to try them. Okay, 11 is metathesis, 12 is isotopes and that kind of stuff. 13, 14, no. 15, no. 16, no. 17, no. 20 is redox. CO2 can be combusted further to form CO3. So carbon dioxide can be combusted further to form carbon trioxide. True or false? False. Carbon trioxide, carbon would be in what oxidation state? In other words, why is this false? Or just tell me why it's false. If you can tell me why it's false, then I can throw in another question that's totally different than this, but you should be able to get it because it's the same concept. You can't go further than what? Plus 4. So that would be plus 6. It only has 4 valence electrons, so it leaves out. Going to plus 6 means it has to lose core. The oxidation state of chlorine varies from -1 to plus 5. You have the periodic table. That's false. It varies from -1 to plus 7. That's right. 22. When aluminum is oxidized, AlO2 is a potential product. That's false. Why is that false? Aluminum should vary from what to what? Plus 3 to -5. This would be aluminum plus. Plus 4. Carbon 12, it's isotopes. The reaction fluorine plus sodium iodide fits the single replacement pattern, A plus Bx. False. False. In the A plus Bx pattern, A is the reducer, B is the oxidizer, X is the spectator. But can fluorine be a reducer? No, fluorine is the most powerful oxidizer chart. Gas formation is a driving force for redox reactions. False. Gas formation is not gas formation is the driving force for metathesis reactions. What's the driving force for redox reactions? Yeah, stronger oxidizer to weaker oxidizer, stronger reducer to weaker. So stronger, weaker oxidizers. 27, write the balance equation for the complete combustion of methane. So complete combustion, we know that when we combust this, it's going to go to what? Yeah, combustion is, we're going to have to burn it in oxygen, and it's going to go to CO2 and water. So we have to figure this out. We need the states here. Oxygen is gas, methane is gas, gas, and liquid. Then we could balance it, 1 carbon, 4 hydrogens, so we need 2 of these, that gives us that, 2 oxygens. We balance it. Lead metal and hydrochloric acid. What is that? Lead metal formula. PbS and hydrochloric acid. HCl. This looks like a single replacement, and in fact this is not one of the exceptions. What this is going to form is PbCl2 plus H2 gas. It turns out not to be one of the exceptions. The way you can figure it out is lead is a pretty good reducing agent, and H plus is a pretty good oxidizer. The only other species we have in there is chloride and water. Chloride is a very poor reducing agent compared to lead. Lead is much more powerful reducer than chloride, and water is much weaker than lead as a reducer, and it's much weaker than H plus as an oxidizer. So this is not one of the exceptions. So this works. But if you don't want to know that, then what we'll do is an inventory. And so what we do is just inventory. We have lead, we have H plus, we have Cl minus, and we have water. And then you pick the strongest oxidizer. Strongest oxidizer present is going to be H plus. You pick the strongest reducer present is going to be lead. Well, that's what single replacement form tells us. And so we can just write the half reaction. So we can use the half reaction method here. Both of these half reactions should occur on the chart. Or we could use a single replacement for this one. Acetic acid and calcium carbonate is metathesis. Barium nitrate and ammonium sulfate is metathesis. Carbon is burned in air. That's redox. Carbon is burned in air. So carbon solid and air has oxygen. What do you predict will form here? CO2. But under certain conditions, we might also get, carbon monoxide or whatever else. So we got two oxygens, one carbon, carbon's balanced. Sodium metal and aqueous potassium chloride. Sodium metal and aqueous potassium chloride. Sodium solid and KCl. Hey, this looks like a single replacement, right? This looks like a single replacement, but it's not. Why? Well, sodium's a great reducer. But according to single replacement, what would the oxidizer be? Potassium ion. Well, we got to know something. We got to know that there's something else present that's a better oxidizer than potassium ion. What else is present that's a better oxidizer than potassium ion? Water. Water is a better oxidizer than potassium. So single replacement is going to fail here because single replacement called potassium ion is the oxidizer, whereas I know that water is a better oxidizer. And so this one you could only do by inventory. Water. And then you pick the strongest reducer, sodium, which is fine. But the best oxidizer is not potassium ion, the best oxidizer is water. So this is why single replacement fails for this particular reaction. So we have to use the half reaction method for this. So but the half reaction, we just copy the half reactions. We copy the half reactions off the chart. Sodium goes to sodium plus an electron. And then copy off the half reaction here. Water, 2 waters plus 2 electrons yields H2 gas plus 2 hydroxide. Just copy it off the chart and add them up. And then look for driving force, see if there's a driving force. What are the chemical properties of HNO3? Well, the chemical properties of HNO3, we can do the redox properties. We can do the redox properties. H plus is an oxidizer. H plus and nitrate is an oxidizer. It's an even better oxidizer, H plus and nitrate. Yes. Nitrate is only an oxidizer because nitrogen's maxed out. Nitrogen's maxed out at a positive oxidation state of plus. What does nitrogen's oxidation state vary? This nitrogen is plus what? Oxidation state? Plus 5. What's the max on nitrogen? It's on the periodic table. Nitrogen varies from -3 to +5, so nitrogen's maxed out. It can't lose anymore. The only thing nitrogen can do is to gain, and therefore nitrate's only an oxidizer. However, nitrite can go either way. You know, what's the oxidation state on nitrite? Remember how to do these oxides like this kind of thing? You know, this is just bookkeeping for electrons. And nitrogen plus something -4 equals -1. So nitrogen must be plus X. Nitrogen must be plus +3. +3 -4 gives us -1. So if nitrogen is +3, then that means it could lose or it could gain. So nitrite is both. Both an oxidizer and a reducer. It could either gain or lose. Whereas nitrate's only an oxidizer. It's already maxed out. Okay, let's go on to the other sample test. Let's take a look at this quickly. So I'm not really going to review. We're just going to go through the answer. Unless you ask me to stop, then I'll explain it. Electrons in the atom are in fixed orbits. False. Hydrogen lamps were expected to emit white light similar to incandescent tungsten light bulbs. True. The 211 NLM orbital is forbidden. False. This is a 2p orbital. Quantum numbers originate from the Bohr equation. False. One did, the N did, but the LM came from not the Bohr equation, it came from the Schrodinger equation. Quantum numbers originate from the Schrodinger equation. 6,563, 452, and 0, NLM is forbidden. True? It's false. It's allowed. We're allowed all values of L up to a max of 6,562. So that would be the biggest L value. And then this ranges from -452 to +452, going through all the integers, including 0. So this is allowed. It's allowed.
So the 6, the N would be 6, below 6.
No, 6,563.
I thought that was
Sorry, yeah, 6.
As like the 6th level.
Oh, no, sorry. Okay, if that were the case, let's say, then this would be forbidden.
Yeah, I thought
That would be forbidden. We're allowed N values up to infinity. 6, 7, 1, -1 is a p orbital. True. L equals 1 is P. 7. Potassium is harder to ionize than sodium because of its many protons. Potassium has more protons than sodium. That's true. Is potassium harder to ionize than sodium or easier to ionize? What does the ionization energy depend on? The Starts with an S. The size, which one's bigger, sodium or potassium? Potassium is a lot bigger, right? It has another shell. So it's easier to take an electron from a big atom or from a small atom? Big atom. You know, you'd think it would be harder to take it from a big one, but the big one, you know, the electron's far away from the nucleus. The nucleus is trying to control everything. The electron gets further and further away, then it's easier to take. So this is false. How many orbitals are there in the L equals 6 sublevel? If L equals 6, then M equals what? If L equals 6, then what are the possible M values? M's going to tell us the number. Negative 6, negative 5,
negative 4, 3, 2, 1, 0, 1, 2, 3, 4, 5.
well, how many is that? That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. E. 13. There's a mathematical pattern. The number of orbitals is 2 times L plus 1. 2 times L plus 1. The plus 1 is a 0. Those are going negative, positive, 0. So L equals 50. How many orbitals are there? There are 101. L equals 1 million. How many orbitals are there? There are 2,000,001. 9. The number of valence electrons for argon core 4s2 3d8 is 2. But some of these cores could react because this is not a filled subshell. It's a partially filled subshell. So we'll take the valence for sure. So it's plus 2. And then we might be able to take some core. 10. Methane plus 2 O2s yields CO2 plus 2 waters. How many pounds of methane? So this is stoichiometry. How many pounds of methane burn for every pound of CO2 formed? So we have 1 pound of CO2. Then we're going to go from pounds of CO2 to grams of CO2. Then from grams of CO2 to moles of CO2 to moles of methane, moles of methane to grams of methane to pounds of methane. And we can figure it out. So for every pound of CO2, CO2 weighs more than methane. It's like this. It's one of these. W, B, E, or C. Did somebody calculate it? This is nitrogen plus 3 hydrogens equals 2 NH3. What mass of hydrogen is required to make 25 grams of ammonia if the percent yield for this reaction is expected to be 88.8%? This is a stoichiometry problem. We don't have time to solve. Why don't you solve and post your answer on Piazza and check it. 12. This is glucose. Glucose plus 6 oxygens yields carbon dioxide and water. Delta H for this reaction is minus 2.82 times 10 to the third kilojoules. What mass of glucose is required to produce 1,000 calories? This is a food calorie. 1,000 food calories is equal to 1 food calorie is equal to 1,000 chemical calories. 1 chemical calorie is equal to 4.184 joules. So this is a dimensional analysis type problem. We'll go from 1,000 food calories to chemical calories to joules, and then from joules we'll use this. Oh, actually, from joules we'll go to kilojoules, and then this is kilojoules per mole of glucose. 1 mole of glucose. This is photosynthesis here. Photosynthesis, CO2 plus water yields glucose plus oxygen. Calculate the percent yield if 5.2 grams of CO2 yields 2.8 grams of glucose. So percent yield, 5.2 grams of CO2 is going to give us theoretical yields of glucose. And based on that theoretical yield, if our actual yield is 2.8 grams, then we can calculate the percent yield. stoichiometry problems there. 14, n equals infinity is allowed. That's true. 15, BF3 contains a double bond, you get an octet boron. That's false. Question yesterday. 16, Heisenberg determined that the electron's position must be given by an electron probability cloud. True. Yeah. 17, modern day scientists visualize electrons occupying orbits around the nucleus. False. 18, 2D orbitals are forbidden. True. Those are forbidden. 19, orbitals describe the energy and positional probability of electrons in atoms. True. 20, oxygen has a higher ionization energy than nitrogen because it has more protons. Yeah. Right side is small. That's in the same shell. That's true. This is true, but you know, I shouldn't have picked this one because this is one of the exceptions. So that's my bad. But yeah, it should be true. It's in the same shell. Oxygen's smaller than nitrogen. 21, the fourth shell of a multi-electron atom contains how many subshells or sublevels? Fourth shell contains how many subshells? 4s.
Oh, that doesn't include 4p, so 2?
Yeah.
That's not 4p.
Okay, well the fourth shell is the 4s, the 3d, and the 4p, just 3. 3D orbitals violate quantum mechanics because of L. Because of L. 3D orbitals are allowed. Those don't violate quantum mechanics, so this is kind of a weird question. 3D orbitals, it's false because 3D orbitals are allowed. 2D orbitals? Yeah, 2D orbitals violate quantum mechanics because of L. That's true. 23, the electron configuration for nickel is argon 4s2 3d8. That's true. The electron configuration for nickel 2 plus is argon 4s2 3d6.
When there's an ion, do you have to add anything to it?
No, we take 2 electrons away. No, it's not true. It's false. Why? It's false because we took them from the wrong orbital. We have to take them from the orbital that's furthest away from the nucleus. The orbital that's furthest away from the nucleus would be the 4, not the 3. And so this should be argon 3d8, and the 4s would have been stripped off because the 4s are going to be the farthest. The biggest orbitals are going to be the easiest to plug off. It's weird because it's reversed. You fill the 4s before you fill the 3d, so it seems like they're closer. But in one way they're closer, and another way they're farther because of the shape. 25. The electron configuration for the fluoride ion is helium 2s2 2d6. Fluoride has a filled shell. The second shell is filled. And so this is true.
But it has a minus on it.
Yeah, but then it just becomes neon, right?
Yeah. And so helium 2s2 2b6 is equal to neon. Equals neon. Because this is the second shell. The second shell is filled with an octet. And so it's just another way of saying neon. The first shell is filled with helium. The second shell is filled 2s2 2b6. Bromine. Xenon 4s2, 4p5. 7 valence electrons. Is that true or false? It's false. It's false because it's actually argon. Bromine argon. 1, 2, 3, 4s2, 3d 10, 4p 5. And so bromine should have been argon, 4s2, 3d10, 4p5. It's false. It's wrong. 7 valence electrons is correct, but the other part is false. Which bond is least polar? The HO, the HF, or the HN? HN. The charge on the halide ion is, halide would be the halogens. -1. 29, core electrons do not participate in chemical reactions.
False.
This is debatable. It depends. If you're talking about transition metals, yes, core electrons can participate, like the Ds are considered core inner shell. However, but for most everything else, this would be false, because only the valence. We're only gonna. This is why, carbon goes from +4 to -4, because we're either removing all the valence electrons or we're completing the valence shell. We're going to go one way or the other. And so we aren't touching the core. And so for the most part, for main groups, this is true. For transition metals, we might or we might not take the D, which are considered core.
So it's true.
Yes, it's true for most of the elements we're doing. So true would be a good answer, but it's tricky. 30, bonds and hydrocarbons are best categorized as, well, you have to know what a hydrocarbon is. A hydrocarbon is a compound of hydrogen and carbon. So hydrogen is at 2.2, carbon is at 2.6, the difference is 0.4. 0.4 means it's non-polar covalent. Non-polar covalent. But in other words, all hydrocarbons are non-polar. What is the predicted, bond angle? No, we're not doing that. No bond angle, no shapes. 32, helium has the highest ionization energy of all elements. True. Skip. 34, how many resonance structures does bicarbonate ion have? Remember, we drew 3, but one of them was no good. Remember? One of them we X'd out. So bicarbonate only has 2.
So to determine a good structure, the formal charges, does that have to play? The formal charges has to be 0?
No, they don't have to be 0, but the one we eliminated for bicarbonate is this one, where one oxygen was negative, the other oxygen was positive. So how can one oxygen lose and the other one gain? They're both equal in strength. So this is why one of them came out wrong. This is it. This was the structure we eliminated. Actually, we eliminated this structure. Oh, no, not this. We eliminated this one. But the other 2 were good. 35 skip, 36 skip, 37 skip, 38, write the electron configuration for silver and silver ion. So silver, we could just use the periodic table, and silver ion, we could just use the periodic table for that. Do that. For silver, which is 8G, here. So we back up, it would be krypton, and then 1, 2, 3, 4, 5. 5s2, 3d, oh, 4d. 40, 1, 2, 3, 4, 5, 6, 7, 8, 9. So silver would be krypton, 5s2, 4d9. But maybe you remember, what was the exception? Chromium and copper. But this turns out to be an exception, because what happens here is that it becomes, 5s, 1, 4d, 10. That's because we're only one electron short from filling the d. And so we expected this is what's observed. It's just like copper. And so that means silver has how many valence electrons? 1. So silver would have 1 valence electron. If it loses that 1 valence electron, we form silver ion. Silver ion is going to be krypton. Well, where are we going to lose that 1 electron? From the 5 or from the 4? From the 5. So silver ion would be krypton 4d10.
Isn't it plus, so you add?
No, plus is losing. Plus, if there's a plus charge, we lost an electron. We don't have to rectify this, do we? Are we out? Well, I guess we're out of time, huh? Oh, yeah, I went overtime. Well, anyway, 39 is a skip. 40, 40 is a stoichiometry. 41, forget the hybrid for right now. You should be able to draw the resonance forms for NO2 minus. 42, yes. You should be able to draw a detailed orbital energy level diagram labeling things. So 42. 43, skip. All right, so if you have more questions, post it on Piazza, or if you have the answer, if you want to check the answers, post it on Piazza. I'll check it.